Welcome back. We are now heading off to 16.2, entropy. Here we're going to define entropy, explain the relationship between entropy and the number of microstates, and predict the sign of the entropy change for chemical and physical processes. So we've been talking about spontaneity, but there has to be some factor other than energy that's important to the spontaneity of a process. So we saw in the last section that greater, more uniform dispersal of matter and energy can be a driving force of a process to make it spontaneous. The other factor is called entropy. So one thing we need to define first is a reversible process. And this takes place at such a slow rate that we consider it to always be at equilibrium. So we can change the direction of this process by an infinitesimally small change of a condition. And no real processes are really truly reversible. So the change of this new quantity depends on the initial and final states of a system, and we call this entropy. And we abbreviate entropy with an S. And the change in entropy, delta S, is equal to the Q, or for the heat of the reversible system, divided by the temperature in Kelvin. So spontaneity is favored by an increase in entropy. So another way to think of entropy is disorder. And so we have this equation for it. S for entropy is equal to K ln W, where K is the Boltzmann constant, and W is the number of microstates that are possible. And these are specific configurations of the locations and energies of the particles in a system. So if we change the entropy of a system, then we have some delta S, an S final and an S initial. And we can go ahead and derive this equation going, okay, K times the natural log of the final number of microstates minus K natural log of initial. And that simplifies down to K ln WF over WI. And we can find the number of microstates given by little n to the big N power, where n is the number of boxes. So you kind of think of these as, I guess, domains, and the big N is the number of particles. So little n to the big N power gives you the number of microstates. So these are those configurations of the locations and energies of particles in a system. And so where these came from was the research done by Nicolas Léonard Sadi Carnot, or the Carnot engine, some of you may have heard of, and Rudolf Clausius as well. So let's think of two particles distributed between two boxes. So that means two particles, so little n equals 2, and the number of boxes, big N, is equal to 2. Oops, other way, sorry. Big N for the number of particles, and then little n is equal to our number of boxes. So our number of microstates is 2 to the 2, which is 4 microstates. And so that's what each of these boxes here represents, is these 4 configurations that are possible. Now, if we have 4 particles between 2 boxes, so 4 particles gives us big N of 4 and little n of 2. That means we have little n 2 to the 4th power gives us 16 microstates. So we're going to see this on the next slide, but when you have microstates that have equivalent particle arrangements, we group them together, and these are called distributions. So we have a total of 16 microstates with 4 particles between 2 boxes. And here's all these microstates. So each rectangle there is divided into 2 squares, and each of those squares in it represent the boxes. And so what you might notice is letter C this distribution here has 6 identical microstates. Okay. So one thing that you can also look at is the probability of finding the different configurations. So for instance, the probability of finding one, getting a distribution like C, you have 6 potential divided by a total of 16 microstates. So you have a 6 in 16 chance, or 3/8 chance. Whereas to get something like one of the microstate in A, you have a 1 in 16 chance. So we have the highest possibility of winding up in like the C-type distribution versus the others. And so like I was just saying, the most probable distribution is going to be C. So some of you might be familiar with statistics and data distribution. This looks a lot like a Gaussian curve. I dealt a bit with this type of stuff in grad school, so when I see stuff like this, I always think of distributions. I looked at size distributions of particulate matter. So the most probable distribution has the largest number of microstates, and it is going to be the one that has the greatest entropy. So if we look back here, what we see looking at these different distributions is the ones that are in C, those particles are the most spread out and more randomized, whereas the others, there's a little bit more order, or some of them are closer together instead of being more spread apart. So we like high entropy because it's the most probable configuration. And this applies to all systems, including those that have larger numbers of particles. So entropy is a state function. So think about what a state function is. We've talked about these before. We talked about it in Chem 1 also. Hint, hint. State function, well, I guess I'll just kind of refresh your memory. State function, it doesn't matter how you get there, you'll get the same answer. So it's like getting to the top of a mountain, getting that elevation, say it's I don't know, 1,000 feet high. I know that's not high at all, but whether I take a magic elevator and go straight to the tip of the peak versus walking up a ramp that slowly circles the mountain and gets to the top, no matter what, I get to 1,000 feet up. I don't know why there's that alternatively, because we already looked at that. Okay, so we do have some factors that influence entropy. The first one being the phase of the substance. Okay, so a solid is going to have a lower entropy than a liquid, is going to have a lower entropy than a gas. Okay, because entropy, again, is all about disorder. And, I mean, chaos, really. You have a gas, and those particles can go everywhere and wherever, and like wherever they want to go. A liquid, they're able to move around some more, whereas a solid, they're confined to a set volume and shape. Temperature also influences entropy. So if you remember, temperature is proportional to the average kinetic energy of the particles. So if you increase the temperature, you're increasing their kinetic energy. They're moving around more. So now they have greater freedom to move around, and therefore higher entropy. I mean, you can kind of think about this with like a classroom full of kindergartners, right? You give them some sugar and they start running around like crazy, right? They've increased their kinetic energy. And what ensues? Chaos. Bunch of children running around, bouncing off the walls, probably literally. Chaos. It is just all about entropy. And then just a little side note nerdiness from me. My buddy did a one-off D&D campaign that I got to join before he left for grad school to the East Coast, and my character was a think I made a gnome. And she was a follower of this like entropy temple thing, and she was like, I think she was called like an agent of entropy. It was really fun. She was crazy. She had a twitch. She never stopped moving. Okay. Um so this is showing heat flowing from a hot object to a cold object, and these are again those microstate models. And so you can see the different potential ways that the heat is flowing. So here's an example. We want to calculate the change in entropy for the process that's being described. So what we first need to do is look at the microstates. And we see that we're starting with one microstate, okay? And then we're ending with 1, 2, 3, 4, 5, 6 microstates. So delta S is equal to K times the natural log of W final divided by W initial. And that's K is the Boltzmann constant, 1.38 times 10 to the negative 23rd joules per Kelvin, times the natural log of 6 over 1. And so this then becomes 2.47 times 10 to the negative 23rd joules per Kelvin. So we have a positive change in entropy, which makes sense. We're increasing our entropy because we're increasing the number of microstates available. So like I kind of talked about with temperature and entropy, the effect of temperature is on entropy is due mostly to phase changes. So I take a solid and it becomes a liquid. The entropy is increasing because it's losing order. Solids have an order about them, right? They have an ordered solid, and then it becomes this less ordered liquid, and then even more entropy as they become an even less ordered gas. Now, if we do the reverse process, going from gas to liquid, we're decreasing our entropy, and then we're decreasing it even more as we go from liquid to gas. And then here's also showing you entropy versus kinetic energy. So the first graph, you see fraction of the molecules versus kinetic energy. So as you have this higher temperature, you have a greater distribution of kinetic energy. You have the higher overall energy. And then you look over at the next graph where you have entropy versus temperature, and it looks a lot like a melting curve, right? You have solid, liquid, gas, and you can see the entropy going up as our temperature is increasing. It looks like a melting curve kind of on its side, right? Whereas when we looked at melting point curves, when we were melting, we had the temperature stayed the same, which is happening here too, but that was on the y-axis. So just kind of a cool thing to see. A couple other factors that influence entropy: the type and the number of particles that make up the substance. So if you have atoms, heavier atoms have greater entropy than lighter atoms. Okay. And this has to do with the particle's mass and quantum stuff that is way beyond this class. And then if you have a molecule, more atoms in a molecule give it more ways that the molecule overall can vibrate, meaning more microstates, meaning higher entropy. And the types of particles. Is it a pure substance or a mixture? This also is going to affect the entropy of a system. So if you have a pure substance, all your particles are identical. So it's going to have a lower entropy compared to a mixture where you have more particle types. So more particle types mean you could have more interactions, more orientations, more chaos. All right. Also dissolving something. So going along that line, if I take salt, solid salt, sodium chloride, dissolve it in water, I'm increasing entropy because this dissolution is happening where now the salt is spreading out and forming this mixture. So I have a quick example. We want to predict the sign of the entropy change for these different processes and say why. What's our reasoning? So in A, we're told 1 mole of liquid water at room temperature going to 1 mole of liquid water at 50 degrees Celsius. So this is going to be a positive change in entropy because we are increasing our temperature. Increasing temperature, those molecules are moving faster. The next one, we have silver plus and Cl minus combining to form solid silver chloride. So this is going to be a negative change in entropy because now we've reduced the number of ions in solution. Okay, so we've taken them out of solution and decreased how matter is dispersed. C, we've got C6H6 and 15 halves O2 going to 6 CO2 plus 3 H2O. It's a good old combustion reaction. And this is actually going to be a negative change in entropy, and that's because we have 15 halves, which is 7.5 moles of gas, and going down to 6 moles of gas in total. Okay, 7.5 moles of oxygen, 6 moles of carbon dioxide, but just total numbers of moles. We're reducing the amount of gas. And gaseous species we know have much higher entropies, so less gases, lower entropy in the system. And then D, we have solid NH3 going to liquid NH3. This is going to be an increase in entropy because we have a phase transition going from solid to liquid, which is going to increase how the matter is dispersed.